Welcome. This is the Engineering B47, first of a couple of Excel projects that we are going to do. This one you will need the tensile test data that is available on Canvas, and we can get going. So in class you're going to hear a little bit about tensile testing, and you'll probably get to do quite a bit of it if you take the materials course. But for this class we just have some data and we're going to do some analysis on the data. Our goal is to produce a graph that looks like this with a mean or average Young's modulus, and we'll talk about what that is both in lecture and then as we progress here, and ultimate strength. So to do this, you need the data that's available, the tensile test data file on Canvas. So if you open that up, you will look like this. I know it's just 4 columns of data, data point, time in seconds, extension in millimeters, and load in newtons. The very first thing that we should probably do is rename this and save a copy of it to our H drive so that we don't lose it, or if we mess up our original data, we still have that raw data available. So let's go up to File, save it as, and I think you can see there in the worksheet, I'm asking you to save it as your last name, tensile test results. And then I'm not at BC right now, so I'm just going to save it to my computer, but you should definitely be saving this on your H drive. And there we go. So you can see across the top now, it's got my new file name. I know I'm not messing with my original data, my raw data, that's protected, and we can start making some changes to this. All right, so we can see here at the bottom, there are 5 different worksheets available. I'm going to work through 1.75a. These are 5 different samples of the same material or the same fill on the plastic. So we've collected 5 different data points. I will walk you through how to do the analysis on one of them, and then you can repeat that on the other 4 and then take the average. So let's get going. The first thing I think we need is to set a couple of constants at the top of our sheet. Step 3 of our instructions says that we have an initial length of 115 millimeters, and then step 4 says that our cross-sectional area is 13 millimeters by 3.2 millimeters, so we should probably get that data into our sheet somewhere. So I'm going to, right here, insert a couple of blank lines before my data begins. Right, so I can add some instructions or some constants. I like kind of keeping my constants off to the side. So here maybe I'm gonna write initial length equals, and then tab over to type in the 115 millimeters. Let's resize H. There we go. So our initial length is set as 115 millimeters, and remember we should definitely make sure we are keeping our cells that have numbers in them just the number. That's why I've got my initial length equals in its own cell here in H1, as well as the units here in J1, so that I can use that 115, the 115, as a data value or a number that I can do math with. All right, so then maybe we can call the length and width, or I guess width and maybe depth of our original piece, and that was 13 millimeters by 3.2 millimeters. So we can calculate then a cross-sectional area as the 13. So this is going to be an equation. I need to type the equal sign, the 13 times the 3.2, right? But then that's going to be in what, millimeters squared. And if I look over here in my column, my data is in newtons, which from physics we know a newton involves meters. So we definitely don't want to be mixing our millimeters with our the meters that are built into a newton. So we should probably convert this to meters squared. So this is going to be equal to this one divided by 1,000 squared, because each of those millimeter have 1,000 in a meter. So divided by 1,000 squared gives us our very, very small cross-sectional area in meters squared. All right, so now we have that, our area available in meters square. We are ready to work on the analysis. So the next thing we're asked to do is create a new column, and we're going to call this column strain. And strain is calculated by taking the extension and dividing it by the original length, right? Because the extension, if you are extending 1 inch and you're a 3-inch long piece of material, then that's a pretty big extension, but that same 1 inch on a mile long stretch of road is nothing. So what we're doing here is we're standardizing our sample so that we can compare cross samples, strain on samples that maybe don't have the same initial length. So take our extension values, let's hit equals to let Excel know it's trying to do something. Our extension divided by the initial length, which is up there. And I hit enter. And my strain is going to be some very small value. Here we can see 2 to the negative, 2 times 10 to the negative 7, so it's some very small number. And if I click on that one and I double click the little square, I don't want to have to write that same equation all the way down, so I can double click the little square to send that formula to the bottom. But you'll notice that it has an error, right? So it's saying dividing by 0, well, that's not what I wanted. Let's figure out what happened. So I'm going to click on my first cell, and I like how Excel color codes what we're doing. So we have here the blue divided by the red. And if I come down here to the next cell and enter it, the blue divided by the red, and I can see that because I moved my formula down, it moved my values down, which is right, because we want to go down to the next extension value. But on my formula, then it moves from my 115, which is the original length, it moves down to the width. And that's not what I wanted. I wanted to be using the 115 everywhere, right? But I don't want to type in 115, because if I accidentally screwed up and it was actually 112, then I want it to be able to auto update and correct itself everywhere, right? So instead, what I'm going to do is in my original formula, on where I called that I1 out in my original formula, up here where it says I1, really I want the numbers not to change. So if I put a $sign in front of the number, then as I move around in formulas, it's not going to move up and down. It's locked at 1. Okay, so now that I've repeated that, I'm going to hit enter. It's got my $sign in there. And now I'm going to redouble click on my 0 going down. And there we go. It looks like it's working. So my strain values have numbers all the way down. And if I enter the next cell down, you can see here it's still locked here at I1. Notice I didn't lock the row. So if I were to move left and right with my formula, or the column, I'm sorry, the letter, it could still move left and right. I only locked the number because I wanted it to stay right there at 1 and not move down with my formula. All right, so the next thing we are asked to do is to create a new column of data to calculate the stress. And remember that the stress equation is load divided by area. We have our load here, and we already have our cross-sectional area calculated here. So I think we are ready to go on this. So let's go stress. This one has units, so this should be in pascals for now, because that is a Newton per meter squared. And then maybe we'll think about making that a different unit here in a bit. So let's start with equals our load, so that's our formula, load divided by cross-sectional area. And if I hit enter on that, that's not exactly what I want, because it'll do the same thing when I send it down. I don't want it to be able to move, so let's add our $signs right away. So there is our load divided by our cross-sectional area, and let's send it on down. Okay, and you'll notice that our numbers are starting to get pretty big here, so we might want to actually say divided by 10 to the 6th, and that will turn it into a megapascal. So our numbers stay reasonable. So let's put MPa there. Now our stress is in megapascals. Remember, I didn't put any unit on strain because it was the extension, which is in millimeters, divided by the initial length, which is millimeters, and millimeters divided by millimeters just goes away. It's unitless. But we could say something like that's millimeters per millimeters just to show what unitless unit it has, if that makes sense. So let's take this one, send it all the way down to the bottom, and there we go. Now we've got our stress in much more reasonable numbers. So we've got our strain and our stress, and might highlight these cells here, right click and say delete. I want to shift up. That way my data is right here at the top. I'm ready to rock and roll. Still got all my constants over here. But now the next step it asks us to do is create a stress strain curve. So I'm going to highlight, and holding shift and control is how you, if you hold shift while you select cells, that highlights them. And then if I hit control while I hold my shift, control, and down, that's going to jump all the way to the bottom of my data and highlight all of it, right? Because I didn't want to have to scroll 300 data points down. So now I've jumped all the way to the bottom of my data, highlighted everything, and we can go up to insert and go to charts, choose the scatter plot there, and there we go. It came preloaded with a title because we had titles on our, we had some text at the top of our data, so it guessed that we wanted it. So there we go, there's our stress strain curve. This is, I don't know, a fairly standard looking stress strain curve. And we are ready to start trying to grab some results. We probably should do a little bit of maintenance on our graph to begin with. If you go to the little green plus sign, we want axis titles. So here, the Y was our stress in MPa megapascals. Here on the X was our strain. And then that was millimeters per millimeters if we want to, or it's unitless. Millimeters per millimeters. And there we go. We have now included a stress, or found and generated a stress strain curve for this data set, which was the next step in our list of instructions. All right, so with that stress strain curve there, I think we are ready to start trying to get some results. Misspelled cross-sectional area. There we go. So in our results, we were asked for two things. The first was to calculate a maximum stress using a formula, a built-in formula, so we can maybe make a place here with our constants, maximum stress. We have our stress column, so I think we're ready to use our formula to find the maximum of a set of data. It's just max, so let's type equals max. Open up my parentheses, and it asks for all the different numbers that we're looking for the max out of. So I'm going to click on my first stress data point, and then I'm going to hold shift and control and then hit down, and that's going to jump to the bottom of that data set. I'll hit enter, finish highlighting it, and there we go. It says my maximum stress is 23.25, and then that is in megapascals, just to keep my units, track of my units. So my maximum stress is 23.25 megapascals. And the other result we're looking for is to calculate the Young's modulus. So to do that, we want to find only the linear portion of our data. Right, so here is the linear portion of our data, maybe right here at the beginning. This looks fairly linear here between 0.005 and 0.01 on the strain values. So we're going to try and extract that portion of our graph, get it its own graph so we can put a best fit line on there. Right, so I'm going to do that. Maybe I'm going to make a new sheet. I'm just going to make a spot to dump that data. So I'm going to call this 1.7a. Oops. Here instead of sheet 1, let's right click on sheet 1 and say rename, and we're going to call that the 1.75A linear. Just as a spot to put that data once I extract it. Okay. So I guess our first goal then is we need to find the strain in that linear portion, which I think from 0.005 to 0.01 seems like a pretty decent linear straight portion before it starts being a little curvy at this end. I don't think I want to include this weird jump in here. I think that was probably just the machine loosening or the jaws giving a little bit on the machine, so I'm not going to include that. I'm just going to include maybe between that 0.005 and 0.01. So to do that, I need to find the data, right? So I know it's in strain, and I know I want to keep those values. So maybe one way of doing that would be to use a conditional formatting. We want to highlight cells between. So we're going to be looking for things between 0.005 and 0.01, and light red, that's fine. Whatever standard is, hit OK. And actually, you know what? I should have had my data already selected, so I'm just going to click there on strain, the first value in strain, Control Shift down to highlight it all, and then let's go back to my conditional formatting, highlight cells between 0.005 and 0.01. And hit OK. Now if I kind of scroll down here, there we go. That's where my numbers start being between 0.05, and that's where they stop being less than 0.01. So that is the area where my strain is kind of in that linear portion. So I'm going to grab that data along with the stress values so we can make a new plot. So I'm just copying that data. I've copied that data. Now I can come over here to my linear portion, and I'm going to Control V to paste it. And I'm going to Control Z to undo. I probably should paste them just as values. So instead of going to my paste, I'm going to right click here, and under paste special, my paste option, I just want the values. Because remember, those strain and the stress values were found using a formula. So if we copy them, this is actually just copying the formula, which doesn't have any values to the left to calculate the stress and the strain on. So by calculating just the values, it's just taking, after those calculations were done, what are the numbers? And we can see that it's working, or it seems to be working, because our strain here is, starting at the 0.005 we were looking for, and our stress and impa was then hopefully the numbers that were right next to it that we copied. There we go. And now we can do maybe another insert, another scatter chart, and that sure does look like we have just that linear portion of the graph from 0.005 to 0.01. So let's grab we can find our Young's modulus is just the slope of this line. So we are really just looking for the slope of this line. So I'm going to right click on it, and I'm going to say add a trend line. We want it to be linear. It's already selected at linear, and then I'm going to scroll all the way to the bottom of my trend line options and display equation on chart and display the r-squared value. So there we go. There is my equation, and the slope of that line then is 1350.2, and the units in that's the slope. So that's the rise over the run. Our rise here, the y-axis is in megapascals, and our run strain was unitless. So the slope of this line would be megapascals, and that's it. Right? So we have our Young's modulus then is 1350.2. And you can actually go in there and actually just copy it. We'll see to copy it, and I'm going to go back to my original sheet where I've got all my data all the way back at the top. Maybe I'll put that number here with my maximum stress. This is Young's modulus for this one, and then I can Control V to paste. There's my 1350.2, and that is an MPa. And there we go. We've done the analysis to come up with the maximum stress and the Young's modulus for this sheet. I would like to point out that at the very, very bottom of this sheet, This is the raw data, the extension load, the time extension and load was the raw data from the machine. But if we use the controlled down arrow to jump all the way to the bottom, the computer, the machine that we were getting this data from, actually does have some of that same analysis worked out. So if we look down here, there is our tensile stress at the maximum load. They got 23.25 megapascals. So let's control back up, 23.25. And the maximum stress we found, 23.25 megapascals. So our analysis is matching. If we come back to the bottom of the data, that control down trick is fantastic. Here's their Young's modulus. Young's is, they've calculated it as 1250. And again, ours was, I think, 1350. So we are really, really close to them there as well. Not exactly like we were with maximum, but they probably have used a different subset of the data, or they have some rules that say when to start and when to end for the computer analysis. But there we go. Those are our values that we calculated, and we could begin to, that's the first of the 5 data points. We still have the sheet B, C, D, and E that you would need to repeat this analysis on, redo those steps so that you'll end up with 5 different maximum stresses to take the average of, and 5 different Young's moduluses to take the average of. And that is what you're going to report, or you've been asked to report in this table for the assignment. So the mean Young's modulus and the mean ultimate strength, both in megapascals. All right, so once we've got our results there, we've actually been working for quite a few minutes, so we should probably take the time to hit the save button. There we go, our project has been saved. We've got our first of our outputs. You can repeat that on the rest of the data, and then we will talk in class about how to turn this into a report. Thank you.